Yeah, everything's fine.
Cool. Cool. Thank you so much, Igor,
You're welcome.
to save my nervous system from some problems. Okay. How our today's class will going on?
Today, as Ivan planned, he suggested for you to make a showcase of MuJoCo, how to launch a GitHub repository on Python, VS Code, Anaconda, or something like that, and how to launch some applications. And 1 second, he also told a following pipeline. How to assemble models using URDF and MGSF, about MuJoCo.model, and tell briefly about integrators and entities MuJoCo.model. Yeah.
Okay. Actually, that was a rhetorical question, but anyway, how I imagined the plan of our today's class in my hands. So what will going on? What about I will talk to you. So first of all, I will start with simulations. What is it and why do we need it? So the second step, I will a little bit introduce you into the what the type of on the first plan. I will a little bit introduce you what the type of simulation tools used in the most frequently in robotics. So especially we will talk about MuJoCo simulator. So after that, we will talk about historical background about URDF model. This is like a historical background of XML models itself. So I will explain you a bit about URDF, because without URDF was like the first invention in the model description. I think that it would be much better to firstly explain you what is a URDF, because in all cases, you can find so much URDF models in the internet, because robotic operation system at least use this type of description files, and later explain how to convert to XML. Also, we will consider about URDF what is the limitation of this type of descriptions. I will explain why and what you can do, what is impossible to do, what is impossible to describe in URDF models. So, and later we will consider XML models. This is like will be extended description of robots. I will explain you when you can bring any information about when you can bring any information about how to write your own XMLs in the future. So, in the first steps, I will show you MuJoCo viewer. And we will learn how to visualize. How to visualize your model. So this is like a short introduction what we will learn today. So let's start. How do you understand the word simulation? What is it?
To build a model and test this model in some kind of scenario.
Some kind of scenario. What do you try to what do you try to understand or what do you try to calculate during the simulation, for example, physical simulation?
Maybe the behavior of this model, so it gives me an insight about the behavior of the system in real life.
Yes. During the simulation, you try to predict the behavior of your system based on some knowledge, physical knowledge about your world. So, what type of simulations do you use in the robotics in much more cases? Let's consider the simple example. So you have a two-link manipulator. So what are the simulations you can apply to this model, first of all? What do you learn in the general robotics course? What can you calculate? What type of knowledge you can calculate on this model?
The angles of this.
Yeah, you can based on the knowledge about angles of your model of your robot, so you can calculate the position of the end effector. Yes, and how this task calls when you know the angles of angles inside of joints, and you want to understand what the end effector position will you achieve. How that's called?
Direct kinematics.
Yeah, that's called forward or direct kinematics. Problem. Also exists the inverse kinematics when you know the end effector position and you want to understand what the angles should achieve your robot to make the desired position possible. This is inverse. But kinematics, when we talk about kinematics consider only the trajectory parts of the of your robots. So, but the physical knowledge about your robot, you cannot understand from the forward and inverse kinematics tasks. So, what do I mean when I talk about the physical knowledge? I mean what is the accelerations inside of your model and what is the masses and etc. So the dynamical part of your simulation also you can describe and predict. So how do you for now, how do you solve the dynamic problems? How do you generate how do you make a dynamic model when you started your simulations? What methods do you know about forward and inverse dynamics?
Newton laws or Lagrangians?
Yeah, Newton-Euler method or Euler-Lagrange method. Also, you can use to generate the robot dynamic model. So, and the generalized form for the dynamic looks following like a MQ X double dot plus CQ X dot is equal tau plus J C Q transpose F Q X dot tau. So, and this is the general form of your dynamics. So let's consider these things. So what is M?
Mass.
What?
Mass.
It's mass matrix.
It's not exactly mass.
Mass matrix.
It's like, yes, it's actually it can be like mathematic, but this is like an inertia inside of your system. What is X double dot?
Acceleration.
Yeah, this is acceleration. In which coordinates?
X coordinates.
Which coordinates means
S coordinate.
this? What?
In the global coordinate frame?
In the global coordinate frame, yeah.
Inertial coordinate form, I guess.
Global coordinates. What is Q? This is actually frequently used to describe the generalized coordinate. What is a generalized coordinate? In, for example, in the example with two-link manipulator.
Minimum number of
Minimum number of what?
minimum number of joint position required to denote a configuration, I guess.
So for the two-link manipulator, here, what is the generalized coordinate we will use?
2, I guess. Theta 1, theta 2.
Theta 1 and theta 2. Here it will be our generalized coordinate. Okay, so how do you think? What is C? Actually,
C is a combination of centripetal and centrifugal.
yeah. This is actually in different literature you can see the different notation of this
Product
dynamical
vector, velocity product vector.
yes, and for example, for instance, here this C, this is like bias forces, like Coriolis force, centrifugal, centrifugal, and the last one. What did we lose here? How do you think? Gravitation. So, gravitational forces. So, okay, the first part of the question we have considered. The second part, tau. What is it?
Torque.
What's the torque?
End effector. Sorry. Joint
Yeah.
torque. No, end effector torque.
This is like applied external force on the your end.
Wrench.
Yes. This is external force. And the last one is specifically exists for the MuJoCo simulator. First of all, this is a constraint Jacobian. And this thing is a constraint force. So, what do you know about MuJoCo? First of all, how the MuJoCo do you know that MuJoCo calls like a MuJoCo. Do you know what does it mean?
I guess it's a multiple.
What?
Multiple
Yeah. Multi.
joint
Yeah. Joint and co.
coordinate plane. Sorry.
Now, this is like multi-joint dynamics. With contact. With contacts. So the most biggest advantages of the MuJoCo simulator that it really cool simulates the multi-joint dynamics and take into account the contacts and the constraints of your system. To describe the model, first of all, what do we need? To use MuJoCo, first of all, we need the model of your robot, which you will simulate during to solving the dynamical model. Oh, also, by the same way as forward and inverse kinematics, exists the task with forward and inverse dynamics. So how to formulate the forward and inverse dynamics solution according to this.
So there are two cases given joint acceleration and position of calculating end effector torque.
So the forward dynamics is the task when you want to understand what is acceleration you will achieve if you apply your specific torque to the joint inside of your model. Inside of MuJoCo, it solves the following. Automatically solves the following equation. So the inverse dynamic this is an opposite. У меня занятие. This is an opposite task when you want to know what is the torque you need to achieve needed acceleration on your model. Okay, so the MuJoCo simulator during the simulation solve one of the following problems. So when it makes the simulation step, so for example, it solves the second order dynamic equation, second order differential equation based on the integration, or solve just if you already know the acceleration in your trajectory, so it solves just a system of linear equations. So from which step our simulations begin in the MuJoCo? Actually, MuJoCo is not only one simulator which exists in robotics applications. So do you know any other simulators?
Yeah, Gazebo.
Gazebo simulator.
Then PyBullet.
Yeah, gazebo. Я правильно написал gazebo? Нет, неправильно. Gazebo simulator. It's used, as I remember, in the robotics operation system.
ROS, yeah.
Yeah, and gazebo simulator, it's so popular simulator because it's basic in the ROS. So, and yeah, that's cool because I want to start to talk with you about the models which we need to use to later simulate our system. So, in this case, let's return back to this equation. Here, the torque parameters you can calculate according to some of your control strategy. So the same thing about x double dot, you can also calculate it according to the trajectory you have. So you can make a trajectory in the state space after differentiate it and get the velocities. And after the second manual or not manual differentiation, you can get the acceleration. So the contact function and Jacobian of contact, it depends actually from the specific configuration of your model. So, for example, if your model have inner contact, so have a collision, so it will be different from the previous step. So it's calculated by the inside of the MuJoCo according to the model sizes and model shapes, collision shape especially. So the C, centrifugal forces, this is also calculates specifically for the current joint positions and current, etc. So, and inertia matrix. This is the basic physical parameters about what is the inertia of your model, of your specific model, and what is the mass distribution of mass, where is the center of mass of your model, and what is the moment of inertia inside the model. And model so, and what do we need? And these parameters like mass and sizes and shapes is doesn't change for the whole simulation time. At least because your robot doesn't. You bought a robot. Robots have specific mechanical structure, and this mechanical structure independent from the time. So, and to solve this equation, first of all, we need to determine with which model does we work. So, and understand what is the model sizes, model shapes, model inertia, and masses, and how the links inside of your model connect to each other. So, and the gazebo was. I actually don't know so accurate the historical background of the simulators, but the gazebo stayed the first most famous simulator in robotics. So, and do you know what type of models Gazebo used?
URDFs?
Yes, URDF.
It's SDF, I guess.
SDF, this is extension.
Format. Yeah.
No, this is URDF. So do you know how this is with, it use the models with, you can simply recognize this, that the model is for Gazebo or is for just robots, based on this extension. So do you know how the URDF translates?
I'm not sure, but I think unified robotic description files.
You're totally exactly correct. It's unified robot description format. So, like basic language for the URDF models used XML notation. So, maybe you know the XML notation because it's so much frequently used in the front end developing. So, for example, it's the grandfather of the XML is HTML. So maybe you deal with this at least one time. If you're a programmer, you deal with this format in the so old notation type. So, and XML, this is like a language, how to describe. So XML language, especially formalized like you have some tag, like like element. It should be closed tag. And some text inside this element or value. Or value is equal something. So, and what is the two main elements uses in the URDF file? Do you know?
Joins and links.
Yes, joins and links. So let's consider the joins or links. What do you want? Okay, let's start with links. So link name so what is how do you think what is the inside of the link explanation? What is another element inside of the links to describe the link physically?
Inertia.
Yeah, inertia.
Sorry.
Inertial. Some visual part.
Yeah.
To just visualize the shape, color, etc., etc. And the third one is collision. So, much more information you can get about URDFs. You can get from the You can get from the official link about wiki, ROS.org, URDF XML link. So let me share a bit my screen. The ROS.org. So how the structure looks like. It's like link, specifically name of the link. So for example, for the robot, for the double link robot, it can be the link 1. Inertia consists the origin of your origin. This is like a center of mass of your model. So the mass itself and inertia. So do you know why inertia inside consists this 1, 2, 3, 4, 5, 6 parameters?
Yeah. So with it's for calculating the moment of inertia of a link with respect to another one.
And
Of
why?
a link with respect to an axis. Sorry.
With axis. Do you know why only 6 elements consist here, not 9 elements? Because the tensor of inertia consists specifically.
Others are 0, I guess.
What?
Others are always others are 0.
It can be 0 in the specific case. No.
So inertia with respect to the same axis is meaningless, I guess.
Is the same. This inertia in
it's different axis, like
Yes.
x with respect to y or.
Yeah, that's cool. So we agreed with the first part. The second part, the visual. So here you can describe what is the material to use. This is specifically like a color or something else. So, and describe the geometry. For example, here link have a just box geometry with sizes 1, 1, and 1. Actually, in visual and collision part, when you try to explain geometry, you can use different type of primitives like a box, cylinder, sphere, or mesh. So also exists the tools how to convert your robot from the, for example, SolidWorks or Fusion Autodesk to the URDF notation. And the collision. Collision describes visual and collision. This is a different thing. So, for example, visual information tell you about how your model external model looks like. So the collision will be considered in the case of the collision dynamics. So to detect that you have to detect that you have a collision in your robot. So just to stop joint increasing, if one link interfere when your one link interfere to the another link. So the second one is joints. Joint, if links show the physical parameter, mechanical parameters like mass, inertia, sizes, etc., about give you information about size, inertia, and masses, etc., about your model. So the joint tell you how two links connected to each other. So joint have an origin. When you start to have a type, is it should to move or is it should to stop, etc., etc. So, and some additional physical parameters like dynamic damping, friction, limit effort, velocity, blah blah blah, lower limits, and safety controllers. So, and it shows how the two links connect to each other from parent to child. So, how do you think? What is the limitation? What is the basic limitation of the URDF notation? Actually, it's pretty simple. URDF can describe the following, only the serial robots, and can describe the parallel structures. So, for example, what is the difference between serial and parallel robotics? Okay, for example, this robot like we have a three-paired robot. So this robot is serial.
No.
Okay, then as example, we have a new three-paired robot.
Because it's making a closed loop, I guess. Closed loop with the ground.
Exactly. This robot is open loop. But for example, this robot will have closed loop, at least because it have the rigid connection between these two joints. So, and the main limitation of the URDF models is that you can't, this is impossible inside of URDF file, describe the closed loop connection. Because let me open one simple example about UR3 robot. So this is how the URDF model looks like. So here's a link one, like a base link, how our robot can connect to the this is a link on which our robot starts. So the joint between the base link and shoulder link, the next link. So, and if you will open, and as you can see, here doesn't exist any nesting links. So the structure itself of the URDF files doesn't allow us to make a nesting links like link inside the link. So, and this is the first limitation of the URDF. Also, it's actually hard to describe, but it's actually hard to describe, for example, some sensors or some compliance elements or some elements which have a specific stiffness. So this is the main limitation. Due to this, the guys from MuJoCo invent the just XML notation of the robot. So let me continue showing my screen. So MuJoCo. So, for example, this three-planar robot manipulator. So the structure of the XML and URDF files is different here. So if in the this here also exists the links, but the alternative thing is like a body. So you can also you have a one body and the second body, and the connection between these two bodies according to the joint. Also, you can describe the geometrical parameters. It's not exactly needed to describe here the how it calls the inertial parameters if you describe only primitives, because the default parameters of MuJoCo allow you to just set up the geometry and it will use some default density of your geometry and calculate it automatically a bit later. So here, let's have some let's try to find some similarities between the URDF and XML. So in the body, you can set up the position of your body. This is not specifically position of the center of mass. This is a position of the coordinate system inside of your position of the coordinate system relevant to the world body or relevant to the previous body. So the XML model starts exactly anytime starts with the world body, and inside of the world body you can describe your robot's bodies. So for example here world body and body one connected to some default joint, and how to understand how to write the XML models. Actually, if you want to write XML models, you can anytime use the reference of your use a reference of the MuJoCo XML models. So here describes so much tags which you can use from the beginning to the end. So, and now we will go to some examples, and we will consider some examples when I will try to explain you a bit about how to describe it. But anytime you can just go to this XML reference and see what's the inside, what you can set up inside. For example, body joint. So here, if here write that this parameter is optional, this means that exists some default parameter here. So this is not exactly that you can set up it. So, or the default parameters is Hingle, for example, here, when you consider the type of the joint. So let's go to the simple examples. Let's go from the beginning. To operate with MuJoCo and to write the MuJoCo XML models. Firstly, what do you need? You need to install MuJoCo. MuJoCo available in the PyPI open library. So you can what this means that you don't need to use, for example, Conda to install it. So, and to visualize model and to just firstly set up the what did you write in your MuJoCo model, you can use MuJoCo Viewer tool to visualize it. 1 second. Let's go to another example. I will make a test. Test model XML. I will just copy an examples and show you how to visualize it for now in the MuJoCo viewer. So the simple example, this is simple example. Let's see what this example consists. This example consists some visual parameters like headlight, some assets about materials. So default material will default if you see that the material here is white, it will be white. So option that you can set up your own gravitation, so you can try to simulate, make your simulation on another planet, for example, Mars. Anyway, so, and what is inside? Inside of the world body, what do we see? We see body 1, which connect to the world body according to the free joint. What does it mean? This means this joint, if the joint have a type free, this means that it can be freely move in 6 axes. So have three translational parts and 3 rotational parts. It have inertial geometry. The second body, geometry is box. Box. So we will see one box. And now we will see the second box, and the third body is sphere. So all of these 3 bodies connected to the world body like a free joint, like a free. So let's try to simulate it. So I call to simulate it without code. I use a MuJoCo viewer, and I need to write MuJoCo file like test model dot XML. So this is how these guys will behave here. So what is inside? What is inside here? First of all, you have some file notations, so you can resave XML. This thing is useful when you firstly work with your DF file and want to translate it into the XML. So you can make screenshots, etc., and go out from this thing. So help button showed you what is the hot case you can use to operate with your simulation. So for example, if I will make double click on the model, I can choose it. So if I will click at the same time control button and raise mouse button, I can move this model and see how it will look like. So let's choose another body. So I will rotate it exactly. So like this. So you can also make pause inside of simulation if you want to just see how your model if you want to stop the simulation. You can make reset. I frequently use reload because during my job, I just open two screens, and here I change the model. Here I make a reset. So let's try to change the material here, for example, geometry on the white. So here in assets, name white, it's up the RGBA. This is specifically how to calculate the color. So to set up material, I need to or delete this RGBA, or I can try to set up it before the RGBA, and it will work. Yes. No, it will not work. I need to delete it. Okay, let's reload. Yeah. Let's return back the white and reload. Yes. So this is how to deal with reload button. So sometimes something goes wrong, but it's like in all programming languages, you can try and see what happened. So here you can also change the physics. You can change the type of integrator. So exists different methods how to make an integration. Like earlier method, Rungi put four implicit and implicit fast. So implicit fast is the fastest simulator which exists in this specific module. About what's the difference between the different methods of integration, you can read in the MuJoCo documentation. I will also share with you the MuJoCo. Yes, this. So here you can also set up some algorithmic parameters, so about tolerance, etc. How fast solver will solve your constraints. So and the constraints you can get according to the equality or not quality setup. You can set up equality and equality constraints inside of the XML module itself. I will later show you the closed loop example. So also in rendering is actually useful to understand how here the default body names, but if you work with a real model, so sometimes it's useful to see how your bodies falls. So and see the frames of your different bodies. So and see some basic model elements. So here the square is a joint. This square actually show us that this is a free joint. If you will see later, I will show you how the joint, like rotational joint, look like. So also it can call actuator like tendon, blah, blah, blah. Inertia. I can understand, because sometimes you can make your model invisible, but the inertia you can keep. So this is a good thing to use to just analyze when you set up a inertia or doesn't set up. So equality or inequality constraints show you later, and some visualization parameters, so you can change the sizes of the or scales of your visualization, additional visualization peak. and groups. So some guys make different geometries in different groups. For example, if you want to split the visual part of your XML to the from the collision part, so you can split it into the one group. So you need to just set up in geometry that this group one. Let's try. Do you see? I set up that this geometry goes to the another group and it splits. So sides, joins, also you can make a groups. So you can divide on the different thing according to your according to what you want. So that was the first simple example about when we had just four bodies, like two boxes and sphere, so which was connected to the real world frame according to the free joint. So let's consider the example when we add some joints. So here, as you can see, our world body and body one box and shape connected without joints. So this means that it will rigidly connect. So from body one, no, this means that it will connect to the swing. Let's try to simulate the thing. So we try to show much more by a better way, but it's impossible. So let's see. To the world body, our body box and sphere connected according to the joint of type Hingle with some specific axis of rotation and with some position. So in comparison to the body second frame. So also the most interesting case about the MuJoCo models is it's possible to simulate the tendons. So like some strings or something else. For example, here, what do we have? We have body one weight, body some sides, and connection between these two body on via just Hingle joints. So let me show you example, and I will also explain you what's the interesting case do we have here in this example. So do you see this? So this is a body. This is our body. We have names here: body 2, body 3, body 4, weight. So and here we work with another interesting thing about sides. So side is just geometry without collision, without masses. This is a side like a helping marker. Usually it's used to set up tendons, so to describe what's the side of the via body it should, what's the path the tendon should go through. Or what's the side it should achieve via tendoning. Sites is actually so useful, guys, because it doesn't influence in any cases on your simulation. So, and also you can use sites, for example, to set up, to add, for example, mockup markers or some additional filling elements in filling elements of sensors, etc., etc. So, and let's go to some so much interesting case about quality and about closed loop structures. So here exists the example about quality and inequality constraint. So actually here I turned off the collision. So it makes by the one moment. So I exclude the contact of these four bodies. So if I will comment it and try to reload, so it will work much more physically. So how this model looks like? Let's see. Physically, we have a world body. To the world body connected the link 1. To the link 1 connected the link 2. To the link 2 connected the link 3. To the link 3 connected to the link 4 with the link 4. So you describe the serial manipulator here, but you add the equality constraint, like kinematic link, from the first link to the last link, from the link 1 to the link 4, at the bottom, at the specific point 004. So, and this is how to set up the closed loop structures. You just set up the additional constraint. So let's try to.
Excuse me. How do we know where is 004?
It depends from the how do you set up your model. So, for example, here let's consider the body 1 have a position 000. The body 2 have position 0.500. The next from the body in the coordinate system of body 1. The next have minus 0.5400.
So are we making these models in the SolidWorks or a similar? I mean,
no, this thing was created manually, so it used some simple primitives. So you can just calculate what is the position, and here the H was 004. Let's go to the XML reference, and I will explain you what is the meaning of this H4. Quality. What do we have here? What's the top? We have connect. Connect, body 1, this is the name of the first body. body to name of the second body. So, and anchor is the coordinate of the 3D anchor point where two bodies are connected in the local coordinate frame of body 1. So let's return back to this model and try to visualize in the initial position. So here's the frame, red, green, blues, and let's also see how this guys looks like. So here's a link. Link 1 goes to link 2, goes to link 2, after goes to link 3, goes to link 4, and here the beginning coordinates of the link 4, and here's the beginning coordinates of the link 1. So, and this anchor, this is the position of this point, of this specific point. Let's try to also highlight the quality. Doesn't seem. Let's change the visualization. Total length, like contact with connect. Let's try to move. No. So anyway, this point H4 is here. So, and you need to connect the coordinates about, so this is like how the link 1 constraint, this is link 4 constraint, and in this point it have a contact. Also, we can try to understand better. We can comment. Oh, we don't need to comment the quality actually, because in any other cases, because I turn off the link itself. So let's reload model. So this is link 4, from this to this, and this is link 1. So, and our model, so our link 4, this from this position to this position, and in this position it have a connection. So, but actually, how to choose the anchor point, it depends from your from what do you choose.
So when you say there is a connection, you mean there is a joint?
There is not exactly joint. So, for example, here, from this link to this link, they connect by joint. From this link to this link, it connects by joint. This link to the link 4 is also connected by joint, but to keep the closed loop structure, we need to limit the contact point between the. It's not exactly the joint. This is
okay. So connection is simply a parameter to say it's kind of closing the entire structure.
I didn't get your question.
So connection is a parameter. Parameter. Yeah.
So what parameter? Which parameter? Look,
which signifies connection. Connection between two links.
Yeah, get a connection between two links.
You
can make it according to the joint. You can make it connect according to the quality, to the constraint.
Okay.
So let me, for now, I turn off the equality constraint here, and let's try to run. Do you see what happened? So this in this point, it loses the connection. So due to this, our closed loop structure broke. So let's turn on the equality constraint and reset. So here, this is like a connection that how in which point the link 1 and link 2 connected to each other. So, but this is actually not joined, not exactly joined, because here it depends from the previous structure. So, for example, here was only the hingle joins, and in the end it will also the hingle join, because the motion of this mechanism is only in the only planar. So, but if you in the situation if you have, for example, double rotation problem, so this connection can be not exactly as a hingle. It can be like spherical, but you don't need to describe here that this connection is spherical or hingle or something else. You can just set that the end of this joint should be connect to the end of this joint according to this notation. So okay, we have 8 minutes before the end, as I understood. Igor.
Yeah, we have 8 minutes left.
Yeah. Let me show you the last example about UR3. So, as you remember, this is the URDF model, not XML. So, I will a little bit show you how to convert it to the MuJoCo readable format. So, and you can be free after this. So, specifically, when you just open, you maybe didn't know, but in the internet exists the large URDF files data sets. I think it can be useful for you for the future to make your projects on the already available URDF files. So let's see how the URDF files looks like usually. I will show you an example based on this database. So in my example, I have universal robot here. This is just a comment, don't be afraid. So here something like describes how the gazebo should work with this URDF file. And to make it works with MuJoCo, we will need to do the same thing. So we need to set up the MuJoCo compiler. So I already prepared this model. I add the compilers, balance inertia true. This means that sometimes models can be can have a little bit not suitable inertia matrix. So it depends from the different things, especially from the developer of the model. So, and we need to add some parameters, so like discard visual false. And the specific thing is meshdir. This is the path to your meshes, which you will use in the geometry. So actually the STL model, XML models is a novel invention. So sometimes it works by the not exactly understandable way. So in my case, it worked if I bring the universal UR3 model, put it in the general path and put near to the universal robot URDF the meshes in the specific folder and set up here the mesh. So, and let's try to visualize it. So in this case, it works. You get the specific URDF or your XML model normal. So, and now if you want to add some specific parameters which available only in the XML, you can just save the XML, and if it will save it like MJ model with exactly the same structure as in the universal robot URDF. So you can now you can add here something like motors, sensors, etc., some sites, tendons, etc., etc. What anything you want. So because you converted it from the URDF, so this is possible. So this is URDF and XML have the connectivity in the MuJoCo, so you can use it also during your simulations. So, and also Ivan prepared for you some examples, and these examples in the lecture 0, MuJoCo and models. So he prepared some fancy examples with Nicolas Cage, which I didn't show you, but you can also visualize it by the familiar way. So, do I need to share with you my notes about MuJoCo? I can, actually. So at home, you can try to visualize any other models and try to understand how does it work. So, any questions? Okay, our time is over. Thank you so much for today's class. That was actually pretty hard for me because I was not ready to teach in online modes. Usually I give my classes in offline. So thank you so much for this experience, and hope to see you later, like my colleagues.